The future starts here. One of the world's most modern and sustainable electric locomotives is being built in Munich, Germany, at a 45,000 square meter facility by 1,200 employees. Every weld must hold.
If anything goes wrong here, it can threaten the structural integrity of the locomotive.
Steel sidewalls that weigh more than half a ton. Day in and day out, 16-meter-long, 12-ton locomotive assemblies are produced here. 36 kilometers of cable. This modern electric locomotive is also a rolling data center, built by people and by intelligent machines.
This is a fully automated robot that takes the wire and inserts it into the socket.
All components are assembled here. More than 1,000 Vectron brand tractor units have already left the factory. Every locomotive is a new challenge.
If we don't maintain the appropriate distances here, then the seals won't line up properly.
Test drive on the in-house test track, accelerating and braking on 500 meters, with the power of 23 semi-tractor trailer rigs.
It's a whole different story, of course, when you're sitting on top of power like this.
One of Europe's largest locomotive factories is located in northwestern Munich. Large enough to hold 8 football fields, this facility produces more than 200 locomotives each year. Used in 20 countries across Europe, the tractor unit is one of the most modern of its kind in rail freight transport. The Vectron electric locomotive delivers 6.4 megawatts of power output. That corresponds to about 8,500 horsepower. The locomotive weighs 87 tons, or as much as 15 elephants. It's over 19 meters long, 3 meters wide, and 4 meters high. This tractor unit is a powerful workhorse that can pull up to 35 freight cars with a total weight of over 2,200 tons and a total length of 700 meters. The electric locomotive is a high-performance computer with 35 kilometers of cable and technical components that enable it to exert 300 kilonewtons of tractive effort and reach top speeds of up to 200 kilometers per hour. This is where the construction process begins. The structural steel warehouse takes up 2,500 square meters. Its 7-meter-high, high-level racking contains all components that eventually form the basic structure of the locomotives. Engineer Julian Scheer continuously optimizes the manufacturing processes. He regularly checks every work step.
This is where the fabrication of the locomotives begins. Several thousand steel plates are stored here. A locomotive like this consists of many small parts, which are then transformed during the manufacturing process into larger and larger assemblies, and eventually become a complete locomotive.
Every day, the factory receives shipments of large steel components, up to 13 meters long, nearly all of which come from German blast furnaces. The electric locomotives from this factory are also especially sustainable because they are up to 98% recyclable. Of the 85 metric tons of material, 83 can be recycled. The warehouse provides all of the necessary parts to the shell construction, either by conventional human-operated forklifts or by driverless transport systems, also known as DTSs. Shell construction creates the foundation of every locomotive. The 16-meter-long, 3-meter-wide superstructure. This steel platform ultimately supports the entire locomotive. This is also where workers assemble the 12-meter-long sidewalls, which they will subsequently weld to the left and right of the superstructure. Construction mechanic Francesco Tortora has been welding here for 11 years now.
The weld has to be done properly, because that's what holds the parts together. And if anything goes wrong here, of course, it can threaten the structural integrity of the locomotive.
The welding operations use state-of-the-art laser technology. Francesco Tortora places so-called targets in predefined locations. Based on those target points, a laser-based positioning system knows where to project the outlines of the required components. These lines on the steel parts show welders what they have to attach next and where. Every locomotive is made by hand, while using state-of-the-art technology at the same time.
At the end of the day, we're also proud to see a finished locomotive and know that basically it really is handmade. Not like in the automotive industry, for example, where robots do a lot of the work. I guess that's what makes this job so special.
And the traction unit so versatile, because the locomotive is available in an extremely wide range of designs and configurations. All over Europe, rail transport is getting greener. More and more diesel locomotives are making way for environmentally sound electric locomotives. Germany has set itself the goal of electrifying about 75% of its rail network by 2030, and to support alternative drive technologies. The Swiss rail system is nearly 100% electric already today. This electric locomotive is a jack of all trades, especially in the freight transport segment. Its versatile configurations enable it to travel on nearly all national rail networks throughout Europe and operate with every power supply system. The traction unit is available not only as a pure electric locomotive, but also with an additional diesel engine. An important transition solution until more railways have overhead power lines. Back at the factory in Munich, shell construction creates the superstructure, the foundation of the locomotive. Within 1 to 3 weeks, depending on the order backlog and the scheduled shift operation. Welding at temperatures of up to 14,000 degrees Celsius, the workers work on multiple elements simultaneously. In so doing, several locomotives take form in parallel on 14 production stations. First, the base frame and sides are joined together. Then, the front and rear cabs follow. Step by step, this meticulous craftsmanship creates the substructure of the locomotive. The 13-ton shell is identical for all models. Only later on does the installed technology determine the countries in which a given Vectron can drive and which drive units it will use. Just one sidewall by itself weighs more than half a ton. Lego for railway operations. The many separate components provide a decisive advantage. Several small plates warp less than one large one, for example. The many individual parts will eventually make the resulting locomotive much stiffer and therefore more stable. The finished superstructure is mounted on an assembly bogie, on which the locomotive shell then continues its journey through the factory. It does not receive its own wheels until later on, because they still have to be painted separately, and because this also makes it easier for employees to work on the locomotive. Precision work where small fractions of a millimeter matter, with the weight of 8 cars suspended overhead. The 12 metric ton behemoth must be seated perfectly in place. Otherwise, the sheer mass of the superstructure could wedge it in so tightly that it could never be separated from the assembly bogie again. Each of these cranes can carry up to 50 metric tons. The steel chains are 10 centimeters in diameter. Several miles of track run throughout the factory. In this way, a rail vehicle and a mobile platform transfer the assembly bogies together with the locomotives from one hall to the next. In the next work step, the steel behemoths are first polished and then painted. The blasting shop uses corundum, a crystalline mineral, to give the steel a gleaming finish that reveals any welding defects. Technicians then apply a special protective anti-corrosion coating that ensures exceptionally long service life, even when exposed to the elements. In the paint shop, the locomotives are coated in separate 30-meter-long, 6-meter-wide enclosures. Primer, clear lacquer, and top coat, in what will eventually become the color of the locomotive, are applied in up to 4 applications. About 400 liters in all. These special coatings not only provide weather protection, but also mitigate damage from stone impacts and facilitate graffiti removal. The Vectron electric locomotive traverses the length and breadth of Europe, from southern Italy, across the Swiss and Austrian Alps, all the way to Finland and northern Sweden. The locomotive can travel at speeds of up to 200 kilometers per hour and has the tractive power of 23 semi-trailer trucks. Depending on the equipment options, the price ranges from 3 to 5 million euros. Back in the locomotive plant in Munich. All internal systems will be installed in the final assembly area, step by step, on up to 10 locomotives in parallel. Different country-specific components are installed, depending on where each Vectron will operate.
Now we're in the machine room, without the roof. Here on the right side, for example, we have our compressed air system with its electrical cabinet. So this cabinet here, it handles the braking, which means it controls the braking system. For example, when someone up front pushes the emergency stop button. Then this cabinet here initiates the emergency braking sequence via this compressed air system, because the brakes operate with compressed air. Continuing on through the machine room, we have here the drive motor fans, for example, which are used to cool the drive motors. And when we look a little further on, we have the power converters, which convert the electrical power because different voltages are required. In other words, the voltage of the overhead lines is not the voltage actually used to operate the locomotive. And moving along, here we have the electrical cabinet for the train's security system, which handles the communication with the antennas below and is responsible for safety here in the locomotive.
To control all the electronic systems, a total of 36 kilometers of cable must be installed in each of these locomotives. Here, the lines are being routed in the main cable harness. Each harness comprises up to 100 cable branches, which in turn contain up to 30 individual cables of up to 5 centimeters in diameter and up to 25 meters in length. Each cable has a function such as energize brake or detect red lights on the route. About 60% of these functions are part of the electric locomotive's standard equipment. and the rest are added on a country-specific basis, or at the request of the customer.
We have a very wide range of variants. Every control harness we build here is different, and that's why we decided to manage the entire process using lasers. The laser actually serves as a guide for the technician. First of all, the laser shows where to route the cable in the harness, in other words, which trough it goes into, and then where to push the line through after that. That way, they're already pre-bundled for the next production process.
This modern laser system has been in use for a few years now and prevents errors in the multitude of cables. A modern electric locomotive is a high-performance data center equipped with electrical cabinets, computers, and special software that controls the train. Mobile robots bring all electronic components exactly when and where they're needed, including the warning song, selected by the workers themselves, so the robots won't run into anyone.
It moves along the path here, so everyone knows that the robot is passing through. It's a driverless transport system that distributes our connectors. So we have a centrally organized connector workstation, and the robot goes there, gets the connectors, and then distributes them throughout the hall.
To this workstation, for example, where another robot knows exactly what goes where.
This is a fully automated robot that takes the wire and inserts it into the socket. What's actually happening here? First, the robot captures an image. It then uses image processing to detect the line, and then it knows exactly where to insert it, here in this particular socket. And it does all this fully automatically. Up here, there's also a display showing how the image processing works, how it essentially identifies the individual numbers and then looks them up in a database and says, okay, this line must be inserted in this position.
Just this one robot wires up to 1,000 plug-in connections every day. This finished cable harness will be tested later on. First, a technician verifies the connections, and only then does a software program run for 12 hours to check whether all connections give the right output signals. If everything works perfectly, the cable harness with its thousands of plug-in connections can be installed in the locomotive. Over the past 4 years, thanks to laser-assisted and computer-controlled cable routing, the software has not detected a single fault. And everything is perfect here too. Another huge hall produces the frontal elements of the driver's cabs, the so-called front ends. Later, these will be positioned at both ends of the locomotive. This will enable the locomotive to travel in both directions.
Here we're in our synchronized assembly line for front-end production. This is for the driver's cab, which is where the locomotive driver operates everything. The painted front end starts out here in the first station, and you can see very well here that the window panes have already been glued in. So this is where the adhesive dries. The second station is right next door. Here, technicians install the insulation and even some of the wiring. In the next station, everything already looks somewhat more complete. Some of the first electrical components are also installed here. On the other side, various internal sub-assemblies are also installed. You can also clearly see here the internal cable routing and various covers. And in our last station, we installed the actual driver's control panel. This here is called the element. It's a prefabricated assembly that we also manufacture here. And then comes this assembly, the console, which is then installed here and enables the driver to control the entire locomotive.
The driver's cab is the control center of the locomotive. It includes all the controllers, switches, and buttons used to move the electric locomotive, to slow it down, or to communicate with track, power line, or control centers. This too requires craftsmanship and extensive experience, because a locomotive that weighs many tons cannot operate smoothly and therefore safely unless all of its components fit like a glove and interact perfectly. There's a whole lot of technology under the hood. A rolling server room for Europe's rail freight transport. In the final work step, all components come together in another huge hall. Here, workers assemble up to 10 locomotives simultaneously. In the final assembly area, the cable harnesses, sub-assemblies such as antennas and sensors, the roof elements, and front ends are all installed on the electric locomotives. High-tech and handcrafted. All components are joined securely together with bolts ranging in length from 1 centimeter to 1 meter. An average build time of 1.5 months and plenty of work by engineers and technicians have their price. Depending on the optional equipment, one electric locomotive costs between 3 and 4.5 million euros. In the assembly hall, multiple work steps take place in parallel. At each station, additional components are installed on or in the locomotive. Here, the complete cable harness is being fastened to the locomotive. Laser systems help locate the right connection points. Power cables, compressed air tubing, data lines. Everything must be trimmed and routed individually. Each European rail service has its own specifications, and these require different assembly steps that every worker must master. Once all cables have been installed, then the associated switching cabinets can be mounted inside the locomotive. Up to 16 electrical cabinets for control systems and switchgear can be installed, depending on the technical equipment, diesel engines or electric motors, and the power grid requirements of the countries where the locomotive will operate. The finished inner workings of a modern high-performance locomotive. Systems to control the brakes, motors for cooling, voltage transformers for alternating and direct current for different countries, a fire suppression system, oil and water coolers, air compressors or train security cabinets to brake the entire train, including all rail cars. And the complete driver's cab with all controls for the locomotive driver.
The locomotive also supports a very modular configuration, of course. As you can also see here, for example, the optional equipment might also include a radio, or at the customer's request, a coffee machine can even be included. When it comes to such details, we're really very flexible.
Once everything is complete inside, the next work step follows: the roof elements.
With these roof elements, it's important to be careful when lowering them into place, where the seals fit over one another, and to maintain the correct distances with the roof elements. Otherwise, the rubber joints won't fit. But then you'll see that later on.
In all, 3 roof elements are mounted on this locomotive, which will be pulling freight across Finland just a few weeks from now. Each element weighs 300 kilograms. Everything must fit together with precision, measured in small fractions of a centimeter and according to established standards. Otherwise, rainwater might seep into the locomotive, for example, and damage the equipment inside. Precision work using heavy-duty cranes. The roof must fit properly on all sides. It takes several employees to check it.
When we don't set this roof element down here properly, then that automatically means that the next element won't fit.
Basti, if you want, you can slide the joint a little more to the right.
The thing is, if we don't maintain the correct distances, then that means that the seals won't line up properly, and then one thing leads to another. There's one of these seals, for example, and there are those pins, and then they can get in our way.
The workers install roof elements on up to 15 locomotives per month. Many of the locomotives built here later travel through Germany, Austria, Switzerland, Italy, Bulgaria, the Netherlands, Denmark, or Finland. Sebastian Slisarczyk and his colleague Luka Simic are installers and metal workers and have been working for the company for 4 years now. Every day is a new challenge when assembling these 19-meter-long, 4-meter-high, high-performance machines.
First, the bolts have to fit in. And then, later, you'd better go inside the locomotive and check everything over once more. In other words, to make sure that all the seals were done properly.
The last fractions of a centimeter. If the bolts fit in the threads now, then the operation is a success. A gap of no more than 12 millimeters is within tolerance. The rubber seals are seated correctly. That means the roof is leak-proof.
Fits. Fits. Good.
After 2 hours of highly concentrated work, all the roof elements of this locomotive are also in place. Only one last step assembly remains now. The locomotives are transferred from the assembly bogie to their own wheels. Each of these bogies weighs 18 metric tons. 2 of them are placed under each locomotive. The final assembly step is called the wedding. The train is mounted on its own wheels. They are produced in advance in the plant in Graz, Austria, and delivered to Munich. The locomotive is now suspended on just one industrial crane. The installation technicians must make sure that the locomotive sits exactly on the 8 springs, which, as with a car, ensures stable driving later on. The overhead crane can lift 250 metric tons. The complete locomotive weighs 90 tons. An additional challenge, the springs and dampers are oriented horizontally and vertically on the locomotive. Here too, the stability of the entire locomotive cannot be assured unless everything meets exact specifications. A 15-millimeter gap. It fits. The critical moment, the last fractions of a centimeter. Here is where we find out just how precisely the installation technicians have worked throughout the assembly process. Once everything is finally in place, the locomotive can then be lowered down onto the bogies and securely fastened in the next step. A total of 24 bolts, 16 centimeters long and 3 centimeters in diameter, hold the locomotive and the bogie together. Underneath the locomotive, the bolts are coated with a thread lock adhesive to prevent them from coming loose during operation. The installation technicians would never be able to tighten the bolts enough by hand. And besides, the overhead work would be virtually impossible without a torque wrench. The wedding took about 1 hour. Now the locomotive is securely attached to its wheels. The assembly of the electric locomotive is now complete. Several quality inspection procedures are performed next to ensure that everything works perfectly. Engineer Julian Scher and the quality assurance representative Thomas Granel inspect the entire locomotive inside and out. The locomotive has a special brake system that undergoes a particularly intensive inspection by the 2 specialists.
Here we have the sanding system. Its purpose is to apply sand to the rail just in front of the wheel to increase the friction. So when it's slippery due to ice or leaves on the rails, for example, or an emergency stop is required, then this nozzle pumps out sand blown with compressed air to increase the friction. You might have noticed this effect also in subways or trams. In an emergency situation when full braking must be applied, for example, or also in winter, then sometimes you'll hear a noise like this during braking. Basically, this is exactly the same. The compressed air essentially blows sand onto the track.
This sand spreader is operated from the driver's console of the locomotive. The actuation works via compressed air, which blows the sand onto the rails through tubes positioned in front of both wheels of the axle. An ingenious principle that acts like road grit to increase friction in winter, thereby shortening the braking distance. Altogether, the final inspection takes 5 hours.
Looks okay? Looks really good. Awesome.
The inspection requires keen judgment and extensive experience. The two specialists have already inspected hundreds of locomotives and know exactly what to look for. During the quality checks, the two engineers examine every lever, every electrical cabinet, and every plug-in connector and verify their function. The locomotive cannot be delivered to the customer until all quality standards have been met. The check also includes the driver's cab, the future workstation of the locomotive driver, who will have sole control over the train.
We make sure that all functions, with the switches for example, that they also snap into place, that they work, that it doesn't snag anywhere. He just pounded there again to make sure nothing rattles. During operation, it's important that the driver doesn't hear a rattle coming from somewhere all the time. And of course, we check screws. We look for any trace of oil or whether moisture has penetrated anywhere.
After quality assurance comes the practical test. The plant grounds in the north of Munich has its own test track for this. It's 500 meters long and has a special feature. There are several different track gauges in Europe, and this test track can be set to all of them, from 1,000 to 1,668 millimeters. Engineer Anton Wagner subjects the electric locomotive to a series of tests. Braking, acceleration, does the emergency stop button work? Does the horn sound? And he has to perform these tests in both directions.
This is what we call the driver's desk. Here we have the traction brake lever that you can use to accelerate and brake. This is the driver's brake valve. The locomotive driver can use it to brake the entire train pneumatically. We have electric brakes for when you only need to make minor adjustments in speed. This saves wear in the mechanical brake system, and it also recovers energy at the same time. And here on the right, we have the mechanical brakes. They brake the locomotive mechanically, just like the brakes on a car, with brake discs.
The outdoor test on the grounds also includes a sprinkler system to verify that the seals protecting all train components are watertight. This leak test, too, is performed on every locomotive.
It's really a whole different story, of course, when you're sitting on top of power like this. And I guess it's something that everyone would like to try just once. And here we get the chance to do it almost every day. And not just here in the grounds, but also out there in the field, on test drives and that sort of thing. It's always something different. And that's what makes it fun.
Test drives are also regularly conducted on the normal rail network, where engineers test top speeds and tractive force with rail cars. The electric locomotive is a powerful workhorse. It can pull up to 35 freight cars with a total weight of 2,000 tons and a length of 700 meters. At the end of 2021, Siemens delivered the 1,000th Vectron to Denmark. Additional orders are currently being filled. DB Cargo is already operating 139 multi-system locomotives in the German and European rail freight sectors, thereby saving more than 80% CO2 compared with truck transport. The Switchyard in Munich North. Every week for 31 years now, thousands of railcars have been joined together to form freight trains and sent on their way throughout Europe. 52-year-old Markus Dudek has been driving freight trains across Europe for Deutsche Bahn for 3 decades.
The great thing is that you're actually always moving, and each day is different. None of that daily grind in the office or in some carpentry shop someplace where you always show up at 8 and leave at 4. And that's also part of the attraction.
Every day, 50 trains roll into this freight car loading station and roll away again. It's one of southern Germany's largest hubs for cargo transported by train. In addition to cargo loading, locomotive maintenance is also performed here. Like an automotive workshop, but for trains. Master mechanic Philipp Hiebinger takes each locomotive one by one with this shunting trolley. The advantage of this is that the drivers need not be present to move the locomotives into the workshop. During this 6-hour inspection, the 31-year-old checks liquid levels, replaces filters, and determines whether worn collectors need to be replaced. First, he uses a laser instrument to measure whether the wheels are okay, like checking the tread on car tires.
I'm taking the wheel profile measurement. We always have to make sure that the flange and the running surfaces are okay. I do this with our measurement unit. It does everything automatically and reports the values back to me. If everything works, it shows me that everything is green, and then I know that the locomotive is also okay. And I have to do this separately for each wheel.
During the inspection, it's especially important that everything under the locomotive fits properly and securely. Weathering effects could damage components, a serious safety risk for the entire freight train.
These are our drive motors. Each axle has its own. We also look here, of course, to see if everything is okay, to see if any lines are damaged. Our axle shaft, we have to check that too, to make sure it doesn't have any stone impacts or cracks, because that's very dangerous. If it has cracks, it can break. The same goes for stone impacts. And we don't want a locomotive to get derailed, of course.
And thanks to the well-trained eyes of Philipp Hiebinger and his colleagues, that, of course, doesn't happen. The air conditioning system for the driver's cab is located under the hood. It works just like in a car, but is much, much larger. The heater, the windshield wiper fluid tank, and the windshield wiper motor are also located here. The interior air filters must also be replaced. Inspections like this one are performed at 30,000-kilometer intervals.
Apart from that, there's not much installed up front here because it's exposed to the elements. There's frost, there's snow, we don't want everything to break down.
To look down on the top of the locomotive from above, there are several platforms in the workshop. Here, Hiebinger checks the collectors to see if anything is broken and needs replacement. Each locomotive can have 4 collectors installed for the relevant national systems.
We have 15,000 volts here. At home, it's 120 volts. And it's 1,000 amps of current flowing here. There's less than 15 amps flowing from the wall socket at home. So we're dealing with a huge amount of power here. I'll look this over now. because if something breaks up on top there, then of course there's a risk that the overhead line also breaks, and then we've got major damage. Then there's no more trains or suburban train service for a long time.
The collectors, known as side plates, have a layer of carbon on top, which wears off over time. The underlying metal has very sharp edges and as a result can, in the worst case, tear down the whole overhead line.
These machines never cease to amaze me, and I also like to get my hands dirty when I work. Who wants to sit in an office all the time?
270 railway employees here in Munich North make sure that all incoming rail cars, from automotive manufacturers, for example, are distributed among freight trains. The rail cars roll autonomously over a so-called hump downward onto the track, where they are joined with a new freight train. Locomotive drivers like Markus Dudek then collect the freight trains for their voyage clear across Europe.
Sure, it's always a pleasure while driving, especially when the weather's nice. In general, from the Allgäu towards Mittenwald, or our regular Brenner-Tarvis run. When you drive through Austria, through the mountains, every trip is still an amazing experience even after 30 years.
Over the course of his 30-year career, locomotive driver Markus Dudek has driven everything, from old diesel traction units to the state-of-the-art electric locomotive. He is especially glad to drive the Vectron, because it has amenities such as air conditioning and extensive assistance systems that make his life on the rails easier. The rail cars are still coupled manually. With the introduction of digital coupling systems, this too will soon change. Now, Markus Dudek must verify that all rail cars are connected to one another correctly and that the train is ready to start its journey. Then, it can set off towards Italy. Thanks to the electric drive system, this will save 80% CO2 versus transport by truck. At the border, a colleague takes over. That's why the locomotive is designed for multiple national rail systems.
This is due to the fact that the locomotive is a multi-system locomotive and goes as far as Italy. In Italy, there's a so-called SCMT. That's another train security system, another technology, and it's integrated here. So when we arrive at the Brenner Pass with the German-Austrian system, we switch over to the Italian system, another power system, another train security system. Then the Italian colleague can take over driving and must operate it with his equipment.
The future of European freight transport rolls on rails, CO2 neutral, and also thanks to the Vectron electric locomotive, which is almost completely recyclable and whose modular configuration enables operation throughout Europe. This modern high-performance electric locomotive is made of thousands of sheet metal parts by a workforce comprising 1,200 employees in all. Many weeks of extremely hard work on assemblies that weigh tons in one of the largest locomotive factories in Europe. And gigantic paint booths enable the construction of a technical masterpiece that can transport freight on nearly all European railways. High-performance computer with 36 kilometers of cable and a small power station move this 18-meter-long, 90-ton colossus all across Europe at speeds of up to 200 kilometers per hour. This state-of-the-art electric locomotive is built in Munich and is moving all of Europe further along the path towards a green future.